Everyone says you shouldn't use mean squared error for logistic regression, and you usually get the same answer when asked why. MSE isn't convex. But here's the question almost nobody asks. Is it always true? Because not convex is a strong mathematical claim. It means gradient descent is no longer guaranteed to find the global minimum. Instead, it can converge into a different stationary point, giving us a solution that isn't the best one. So if we're going to build a classification model on top of this idea, we should probably know exactly why it's true, not just repeat it. So in this video, we're not going to take it on faith, we're going to actually prove it. Mathematicians have a property that tells us whether a function behaves like a smooth ball or something much more complicated, and we call this convexity. And here's why we care about it so much. If the loss function is convex, every local minimum is also a global minimum. No matter where we start, no matter how we initialize our parameters, we always end up in the same place. So how do we actually test for this? For a function of one input and one output, there's a simple condition. A function is convex if its second derivative is greater than or equal to 0 for every value of x. So that's the test. Does the mean squared error actually pass it? To prove that a function isn't always convex, we don't need to check every possible dataset. We need to find one valid example where convexity fails. So to keep the algebra simple, we'll let x equals 1, y equal 1, and theta to be one-dimensional. And remember, z is equal to x theta, which is just theta, as x is equal to 1 for our example. The probability used in logistic regression is defined as the sigmoid of z. So for one training example, L of theta is defined as p minus y squared, which is just the squared error. So in other words, p minus 1 squared. Take the derivative with respect to theta, and we get 2p minus 1 times p 1 minus p, as the derivative of the sigmoid is p 1 minus p, and it's multiplied due to the chain rule. We can then expand the brackets and simplify to get 4p squared minus 2p to the power of 3 minus 2p. Take the derivative of that with respect to theta by taking it with respect to p, then multiplying it by p 1 minus p. Now remember, convexity depends on its sign. We know that p is greater than 0, and therefore 1 minus p squared is greater than or equal to 0. So we want 3p minus 1 to be greater than or equal to 0. So or p being greater than or equal to a third. So for this training example, when p is less than a third, the function is non-convex. And that's the proof, ladies and gentlemen. For this training example, when p is less than a third, the second derivative becomes negative, which means the loss function is locally concave, not convex. So mean squared error with logistic regression fails the convexity test, and that's one of the reasons why binary cross entropy becomes the second choice. But why is binary cross entropy convex? Well, this is where one of our theorems can come into play. Rather than trying to prove convexity directly, we can use a theorem. If the Hessian of a twice continuously differentiable function is positive semi-definite everywhere, then the function is convex. I'm not going to prove why that theorem is true in this video. If you want to know why, comment down below, prove the theorem. But before we continue, let's quickly answer one important question. What exactly is the Hessian? Earlier in this video, we used the second order derivative to test whether a function of one variable was convex. The Hessian is simply the multivariable version of the second order derivative. Instead of calculating one second derivative, we calculate every second order partial derivative and arrange them into a matrix. So if you can show that this matrix is always positive semi-definite, our work is done. Now, thankfully, we've already completed most of the mathematics. In previous episodes, we derived the gradient of the binary cross entropy loss and showed that it was equal to 1 over m x transpose p minus y. Since the Hessian is simply the derivative of the gradient, all we have to do is differentiate this one more time. I'm not going to go through each step of the differentiation process, but there will be a montage. and through the montage we can see that the result is 1 over m x transpose Rx, where R is the matrix on the board. Now this matrix is actually very interesting. Every diagonal is simply pi 1 minus pi. Now we can finally prove the Hessian is positive semi-definite. By definition, a matrix is positive semi-definite if V transpose HV is greater than or equal to 0 for every vector V. So let's substitute our Hessian into this expression. Now we'll simply rearrange the brackets. To keep the notation clean, let's define u being equal to xv. That leaves us with 1 over m u transpose ru, and that's exactly why writing the Hessian as x transpose rx is so useful. Because R is a diagonal matrix, expanding the quadratic form is incredibly simple. We get this. Now look carefully at every term in the summation. The first part, pi 1 minus pi, is always greater than or equal to 0 because every probability lies between 0 and 1. The second part, uvi squared, is a square, and squares are never negative. So every individual term in the summation is non-negative, and if every term is non-negative, then the entire summation must also be non-negative. Therefore, V transpose HV is greater than or equal to 0. And thus, we've proved that the Hessian is positive semi-definite, and by our theorem, binary cross entropy is convex. So that's exactly why mean squared error isn't the standard loss function for logistic regression. Thanks for watching, and I'll see you lot in the next one. Take care, bye for now.